Hi, I hope you can hear me okay. I'm in the hotel lobby, so that it's not particularly quiet here. So I think where you're confused is that first you need to realize what Ben did at the beginning of the notebook, and I have to admit that it took me several hours. I first completed the assignment in the wrong way, and then I figured out the beginning, and only then I was able to do it right. So what I think is important to do first, let's look what he does here. So this is just import different things. Okay, this is the first important part. Here he imports the fours and nines into the database. And so here you have arrays of all the images of nines, and here you have fours. So that's important to realize that right here, right now, you have a separate array with fours and separate array with nines. Okay, how can I scroll it? Okay, so for example, if you take 9a with the element 0, you'll see a particular 9. Same, you want to take an element from array force A and you will see the force. Okay, so what he does next? And that's an alternative way to show it, so you can see that it's shades of gray. Okay, so important part is happening here. Let me pick red. Okay. So what he's taking is taking the array that we saw of nines, and this array consists of. Let me try to scroll up, and I hope it doesn't break. Okay. So I cannot do it here because this is not laptop. This is the tablet. But basically, if you were to do the comment nines a dot shape, it would return you something like 28, not 28, at, I don't remember, a lot, like I think 6,000 or something like that. Actually, you know what, we have the answer. Ignore what I'm doing now. Let me see. Okay, so it would be somewhere here, by the way. Okay, but why don't, okay, so here it is. So he's doing this reshape and he removes one dimension. So before it was 6,958 elements, each of which was a matrix 28 by 28. So you can think about 28 by 28 matrix. That's for example your 9, right? And then you kind of have the slices of them, the stock of them, and you have 6958 of those. That was before. Now with this reshape thing, what he's doing is he takes that square that you had, 28 by 28, and he transforms it into a single row. So this part comes here, these parts goes here, these parts go here, and so now instead of having an array of 28 by 28, he has an array of 784, a line. So remember how we had a cube, right? So now instead of cube, we had a sheet of this long lines. So you can think of this like he actually flattened, like he took the that block and he compressed it into the foil sheet. So that what happens. And now what you have nines RA, you have fours RA. Now you have zeros. How many of them? As many as you have nines. Here you have 1, 1, 1, 1. How many? As many as you have fours in fours array. So let's see. 9 tags. I'm sorry, let me restart it. So 9 tags is here, and the shape is this. So you have almost 7,000 zeros. Similarly, you have 4 tags shape. You have 6,824 ones. And remember that all your pictures are stored here, and you know for a fact that those are nines, and you know for a fact that those are fours. You don't need to classify anything, you know this in advance, because these were taken from the database of nines and fours. So here, that's also what he is doing. This is his last manipulations. He concatenates nines and fours are A's, those lines that we saw. So you can think as he used to have this sheet and he puts another sheet here, and so each of the line represents a 4. Each line is here. No, those were nines, those are fours. So each line here represents a 9, each line here represents a 4. And so what he does here is oh my god, where is I'm 9? Where he defines I am 9, I think here. Yes. So here he takes one random 9 from the array, and by using reshape, he takes this really long array. How many they were? Like 784, if I'm not mistaken. And then he reshapes it into 28 by 28 square, and you can actually see it, and it makes sense for a human eye. But computer doesn't care if it reminds us a 9 or not. So then he blends it, right? He also blends the tags. You remember, zeros for nines and ones for fours. And so now all X contains all the pixels, all Y's contains all the tags. So if all Y with the index I equals 1, we know that all X I would return us an array of pixels that are in fact represent a 4. You remember that 1 stands for a shape of 4, 0 stands for 9s. He then uses train test split, and he gets X train, Y train, X test, Y test, and he separates it in proportion 2 to 1. So basically, X train is pixels, X test also pixels, Y train would be tags, so we know if those are 4s or 9s, and Y test also tags, and train test split will split it randomly, so you will have everything 4s and 9s here. You will not get only 4s or only 9s. Okay, now what I did, last part of his code, those are the lines to view any particular line of pixels in a way that it will make sense for a human eye. Okay, let me... So that's how I did it, and please don't copy it word to word in order for us to not break the NYU code of conduct, right? Plagiarism and all that. So first, that's just me. I created the function that would show the picture. Then I took all the 9s that I know are 9s. I also took all the 4s. I know for a fact that this is 4. And then I took this array. Well, no, sorry. I converted the list into NumPy array because I will be using a certain functionality of NumPy, but you don't have to use it. And so then I did the create cluster function. What it does is, I'm sorry, where is it? Give me a second to remember. Okay, so first of all, I create the cluster variable, and I put all zeros. I know that this thing will be 28 by 28. And so I use range shape 1, range shape 2. By the way, if you put 784.1, it will also work exactly same way. So then when it does, it goes, oh, you know what, I'm showing you the old way I did it. I actually then found a better, more elegant way. So you can keep this, and later on I will find the better way that I used. So I'm sorry, where were we? Okay, so what I'm doing is, for a particular pixel, you know what, let me stop here. I basically coming up to the same thing. So no, okay, sorry, let me restart it here. So my idea is to take first all the 9s. So what I'm doing, I'm going pixel by pixel, pixel by pixel. So if you have this picture, it was not 7,000 but something close to it. So I'm going for each pixel. So let me use this one. So I'm taking one pixel, right? X and Y, X and Y. X would be the first dimension, Y will be second dimension, and 0 is this dimension. And then I'm taking this pixel at X, at Y, and I'm going for each eye going into this direction every time. And then I divide it by this amount. So essentially what I'm taking X and Y, like first pixel at each image, and I sum it up. Sorry, it's a lot. I sum it up, and at the end I divide it. So that's how I get the average for each pixel. And so this is, as you can see, an average 9. This is an average 4. As I mentioned, I found a way in NumPy library to do it automatically. So I think this just takes lots of code and highly inefficient, but the idea is the same. By the way, I'm not sure if you should stop here. What you could do is basically you could filter it out and leave only certain parts, right, and use them as your clusters. So later on, just going a little bit further, later on what I did is my god, yes, that was highly inefficient process, so I had to reduce it and took only every thousandth element, so don't look at this. So later on I would calculate the Euclidean distance to this. This will be D9, this will be D4, and then if this one is closer, I would classify a new observation as 9. If this is a better thing, if this is a smaller thing, I will classify it as 4. So that's how I went. Again, I'm not sure if this is a right way, but I think it makes sense.